Okay, I think we might be back. Where's my obs? Okay, obs is happy. Just check my restream, see that that's all happy. It had to happen sometime, didn't it, this semester at least? So this is the first time that we've had my internet just brown out while working. Looks like it's all good from Restream. I don't know what's going to happen on Microsoft Streams. I'd have to say that Microsoft Streams is the most fragile of all of the systems. Whoop. Okay, we're back. Sorry about that brief interruption. So I was just talking about how we're going to deal with arrays and where we're going to put them in memory. Now I want to get to the examples in a minute, but we've got a few more questions to ask. And one of them is, can't we just use registers for arrays, right? I think I've emphasized in this course that you really need to be working with memory from the very first examples. And that's because when we start to deal with things like arrays, they're really not going to fit into a register. So I'm not exactly sure what is going on here, but this is not how you make coffee. You cannot fit the whole coffee into this very small cup. And if you try to do that, you're probably doing it wrong. So I guess if our registers were 32 bits, then we could potentially have a 32 element array where each element was 1 bit each, but that would really not be a lot of information that we want to keep track of. So hopefully, and in fact, definitely, we do want to be using memory for our arrays all of the time. I don't think there's any real good reason to do arrays in registers. Probably not. So here's an example of an array in memory. One's not too complicated. And we're going to use this diagram a lot over the next lecture and on Friday's lecture as well. So just getting my pen out, is that each of these indexes, that's sort of the address within the array, is going to represent the first memory address at the bottom of each one. Of course, we've got high memory up here and low memory down here. This array, index 1, this is, it shouldn't really say index there, it should say element, because this is the element spans a number of bytes. Each one of these squares is a byte. And this is the address of the first element. So the first index is really pointing at that first element, that first byte address. And then each of our elements spans 4 of them. So let's answer our questions. What are the things here? Well, we don't really know that. Where are the things? They're starting at this first address down here, OX2 00000. Hopefully one of the last times I have to say that in the lectures. We'll get beyond these representations maybe. What kind of things do we have? Well, we're not sure, but we know that each element here takes up 4 bytes. Another word for 4 bytes is 1 word in 32 land. The word length of a computer system can be different depending on the system. So some older computers may have a 16-bit word length. With the ARM v7m system, we have 32-bit word lengths. You can have longer ones. It's dependent on the system. Yeah, and how many do we have? Well, I know that we have 8 because that's where we get to our end. So that's information we know. How many? 8. How big are they? Each one's 4 bytes, 1 word. What are they? We're not sure yet. And where are they? Starting at OX 2000, 20000. I have to say it again. Now, the trick with the array is that we can do what we call array addressing, which you know how to do already from higher level programming languages. For instance, you would take in something like C or Java, you'd have an array called the things, all our stuff we had on the previous slide, and your index would be in a little number in a box here, indicating which element of the array that you want. So when it was index 0, that's going to be this first one, element 0. It's going to give you the address of this, or get you back this element which is stuck here. If you're working in C or Java, this will deliver you the item you've stored there. And in this case, now we know what we're talking about. We're talking about ints in each element of the array. And the things, number 4, with index 4 is going to get you the 5th element, right? The 0th element is the first one. 0, 1, 2, 3, 4. And that's the 5th element in the array out of 8. Now let's try this in assembly code. This is where things get a little bit more serious for us, how we can actually do it. Well, we're just doing loads and stores, just like we're used to. You can do all this already. So we've got a list of the things in memory, 1, 2, 3, 4, 5, 6, 7, 8 things. And we've decided that each one is going to be a word represented by one single number. We know that our base address is this one, the things. We don't know where that is. We probably would guess that that these things would be in different places, but we could guess that it's at the bottom of memory, but it could be somewhere else. If we've got our label here, we don't need to worry. We can just use the label. And then if we wanted to do this little function, get some elements, the first thing we do is find what our base address is. Letter R0 is equals the things. Then we get the first element, which is just going to be loading up whatever word happens to be in that first one. Whatever word happens to be in R0. And if we want to get our 5th element, we can just do an offset from R0 to get us all of the way to that first address. Let's just count that off. That gets us to the 5th element. I want to check that. 16 bytes offset. 1 byte offset, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that gets us to array index 4, the 5th element. Now the crucial thing here, this is important, is that our offset 16, we don't just pull that number out of the air or have to count our bytes. We know that each element is 4 bytes long. That's one element. And we know we want to skip 4. So we have to offset by 4 times 4 bytes equals 16. Okay, and that gets us our offset element. Having a bit of a chat in the Teams chat right now about what the difference might be between an array and the stack. So there's a few ideas here. Someone says, isn't a stack one type of array? You can store multiple elements in a stack similar to an array. That's true. Absolutely, you can store multiple elements in a stack. I guess the main difference that I would imagine is that in the stack, your data elements are not always the same kind of thing. So you could use your stack and add words, only words, and everything you're adding is a 4-byte word. But that's not how we always use it. Sometimes you might put 16 bytes of something on the stack, or 32 bytes of something on the stack, and just move the stack pointer down by 32 bytes. If you're only pushing and popping register values on and off the stack all the time, they're always the same kind of thing. They're comparable in some way. But arrays have this property that they have to be a consistent type of thing. That is, they have the same length for each element, and each element can be interpreted in the same way. And if they don't have that, then they're really not an array. They're something different. We have data structures for those in higher level languages, which have more complicated ways of existing. But no, I wouldn't call the stack an array because they don't have that feature that every element of them is the same kind of object or same kind of content. Mitch's explanation, or his suggestion, is that, oh, he said the same thing as I said. Okay, well, we're in agreement. Me and Mitchell are in agreement. which I hope we should be all the time, although we wouldn't always be. Yep, someone else has suggested that a difference between arrays and the stack is that a stack is growable. It's always starts at one point and you can always add and add and add and go down in memory until you run out of memory. You get stack overflow. We can't usually do that with arrays, particularly if they have a fixed length. The array can't expand more than the amount of memory we've given it. And certainly if you read something from an array, you're not making it smaller, so you're not, you don't have this way of deallocating memory. We talk about memory allocation later, so let's not dwell on that now, but we can just focus on what arrays look like and why they are definitely different than stacks. So a few more points to make before we do our full explanation of how to do arrays on your disco board. There's this idea of memory alignment. So you can see in our first array example, all of our memory addresses was really neatly aligned to 4-byte boundaries, or byte boundaries that were a multiple of 4. And you might think, well, why did we do that? It could be that it just happened randomly, that we started at the base address and then started adding 4s to it. And maybe if you just started at a different address, instead of 2000000, you started at 2000001, the same thing with +1. And then you do 4 bytes each time. It's the same 4 bytes, 4 bytes, 4 bytes, 4 bytes. Now, well, you could do that, and there's nothing stopping you doing it on your disco board right now. But we call this unaligned memory, because the elements that you're reading from memory are not on a neat 4-byte or 1-word boundary. And as it turns out, computer systems are usually a little bit limited in how they can extract information from memory. And in general, that the limitation is that they only want to extract it on word boundaries. That's just in general. There's many differences in explanation, in implementations. In fact, on your disco board, it's configurable about whether it even allows unaligned loads and stores from memory. Unaligned meaning loading and storing from any address, not just one on the 4-byte boundaries. And when you do allow unaligned loads, they're slower. They're probably slower because it secretly behind the scenes does multiple aligned loads and gives you the result. When we're talking about a whole computer system which has more memory and some cache lines which are grabbing information from memory behind the scenes so that it's faster for the CPU to access it, it can end up being much, much slower to do unaligned loads because the caching algorithms don't know how to deal with it. It can take a lot more effort. So basically the lesson from this is alignment, good. Unalignment, maybe bad. Of course you can do it, but it could be slower. Oops. Now, so far we've only put things that happen to be word length in arrays, but you can put whatever you want in an array. It doesn't make a difference, right? You know that from Java. You can put whatever object type you want, and C you can put ints, you can put doubles, you can put floats, you can put anything you want. You can put arrays in arrays, no big deal. In this instance, instead of having individual elements that are only 4 bytes in length, they're 8 bytes in length. So we're going all the way up to the 8-byte boundary. And this means that within the same amount of space, we can only store 4 elements. Now, when we go to load this array, supposing I was loading element number 3 at array index 2, when I load the array, I would probably like to grab all 8 bytes. But we can't, because we can only, the loading command only loads 4 bytes at a time. So you're going to have to do 2 loads into different registers. Maybe that one goes into R1 and that one goes into R2. And then in some way handle that value across both registers to make sure that you understand you can do your algorithm with it. So it's going to be a little bit trickier in this instance. We can also have arrays which have smaller sizes than one word. They might have an odd number of bytes, or a number of bytes which isn't a multiple of 4. So for instance, we could have an array of 3-byte elements. And in that case, we now have a choice about how to represent it in memory. One way would be to stick everything together with no space lost in between this way. So we've packed it all into memory. Even though there's only 3 bytes, we're just starting each one at the next byte after that. And that's obviously now going to be unaligned. That's not on a 4-byte boundary. That's not on a 4-byte boundary. That one's not on a 4-byte boundary. Okay. Another option would be to pad each one out. This will make it a little bit easier to read because everyone's on a 4-byte boundary. Now, as I said before, unaligned loads and stores are generally slower, but of course, in this case, there's a trade-off is that you've now saved a lot of memory. And if, for instance, this was an image, maybe each one of these was RGB, RGB, RGB. Of course, your image is going to have a lot of pixels. That's going to take a lot of memory. And you might decide that padding things out in memory is too wasteful. If you had too many pixels, you're just throwing away too much memory and you can't bear that loss. So the space requirements of your algorithm might overrule the loading speed requirements of your algorithm in that case. Just an example, but of course there are many options for how these things should be structured. Adam has said, would assembled code for be a kind of array in the code section of memory, or is there some subtle difference? Assembled code would not be like an array because it's not it doesn't have a consistent size of element. As you know, assembled code can have instructions which are either 16 bits or 32 bits in size. So that's not going to work. Oh, Adam said, apart from the size difference. Well, isn't an array if you're not worrying about the size difference? I suppose in some sense you could think of it as an array, but in that sense you can think of everything. Well, all an array is a sequence of elements in memory that are all the same kind of thing, that all have the same size. So anything that satisfies that property could be called an array in this sense, in this definition of the word. But generally we kind of preserve array for our use as programmers of data structures. So it's not generally used for that. Usually we call the list of instructions in memory this stream of instructions, the instruction stream. And of course it could be it doesn't always make sense, because there might be some chunks which don't have any instructions. They might have some data stuck in there, which could be all kinds of different sizes. And your program isn't paying attention to it as an array, as in going from the start to the back. As you know, the program counter goes everywhere, depending on where your branches are. So I don't think it's that great an analogy to think of it as an array, but in some senses it could satisfy those properties. I want to move forward, but this slide, the idea is that you might have heard about types or abstract data types from higher level languages. And you often talk about which types inherit from other types, what mathematical properties they might have. You could even go into things like type theory, which is sort of a field of logic. But in this instance, we're really talking about something different, even though some of our things do have a type, like an int is kind of a type, it has these mathematical properties. We're really interested in how it looks in memory, or what the data looks like and how we should structure it in memory and take advantage of that structure to write fast assembly programming programs. So really, the abstract data type stuff is not what we're thinking about now. We're really thinking about the practicalities of representing data. Okay, now we're going to work with arrays. And because we know that they don't fit in memory, we're going to just work on them one single element at a time. So this is not going to be too hard. We've already done a little bit of this with the shouting a string element example. We definitely need to start looking at loops. Using a for loop to go through an array is a good idea. Now, if we'll look at a simple kind of array use algorithm in a higher level language, like C or Java, we might have something like this. So the idea of this example is to take an array of integers and to add them all up. Do a sum of every integer of the array. Now, if we happen to have this, we could have this function that takes the array as an argument, also takes the index we start at and the index we go to, and then we create a new local variable to store our sum as we go. And then we just write a for loop for int I equals from index, I less than 2 index, I plus plus. And then at every step we extract one element from the array, have a look at it, and add it to our local variable, and we're done. So that's not too hard. You all understand how to do an array sum. Now we have to do this in assembly language. So first of all, how do we get the array into our code? Well, you've done these already using these .word directives. And this is a good way to do it. So we're going to take .data directive, our array label for it, and then we're just going to make a list of words that will put it into memory. 23006300. And we want to add these up. Now, the actual answer here doesn't matter too much, but it's 14. So it's 6 and 6 and 2. So that's 14. 2363. Now we're going to have to do a bit of setup, which we did before in our program. The first thing we do is grab the base of our array. As we said, where is it in memory? Then we need our from index and our to index. So we're going to store these in two registers, R1 and R2. R1, R2 will be 7. And then we get to move on to our actual algorithm. So if we want to go through the whole list, our base address is there. From address is where we start. And each of these elements of the array takes up a whole word. Now, if you remember when we were doing this before, we were dealing with bytes. So each element of a string or a byte array was just one byte. This time they're a whole word, so we have to skip forward through the array as we traverse it in our loop. And we want to get up to this to index, so that would be 7. And the from index is 0. We could change the from index to be, in this case, 2, and the to index to be 5, and do a smaller array sum if we want to. There's no particular limitation that we have to look at the whole array in order to get anywhere, but we can definitely change those two values as we go. So here's our first go at it. Actually, I'm just going to do this in VS Code. That's more fun. Okay. I need to set up my array. Data, my array. Dot word, what was it? 0, 2, 3. I have to go back and look at the actual list of 2300630. Is that right? Yeah, that's what I wanted. I need to have commas in between those, otherwise it's obviously not going to work. You fool. You must all be shouting from the comments. Okay, cool. And we're just going to do our setup to make sure we have our array in loaded up in a register. And you know we were doing this as want this to be kind of a function, right? So these things are going to be from, to. Yep, someone was shouting at me from the comments about the commas. Glad you picked it. Array address. Okay, and we're going to make another function which will be array sum. BXLR, that's how we finish off a function. Oh, dot text, whoops. Don't forget that. You know we can put the dot data at the top, but then you have to have a dot text after it. Okay. First thing we do in our array sum is set up our accumulator, mov r3, 0. Well, that was array sum number 2. I want array sum number 1. Now we're going to put in, well, we've got to do a few things. We want to know what our element size is. It's 4 bytes. So that'll be the size of each element. And then we're going to have a little loop, which will be something like this, sum loop. The first thing we do in our loop is calculate what our address should be. So we can start with I feel like we've gone off the rails with R5. What's that going on? Oh yeah, that's our offset. So we should start with that at 0. R5 is 0. Who knows if it was something else before? I just want to make sure it's 0. We're going to multiply the size of each element with our current location. Because I'm going to start incrementing this R1 as we go. So R1 is going to be our counter for our counter variable for our loop as well. R1, R4, so this is the offset equals counter times size. Okay, and then we're going to load the element from our array. We'll may as well load it into R6. Now we can do an offset load, R5, grab array elements, and then we can add our R6 to the sum. What was our sum? R3. Results variable. Now we have to increment our index, add R1, 1. No, that's true. Adam Rowland says I don't need to initialize it. Whoops. Don't need to do that. Sometimes I like to just be clear with myself about where my variables are. I'm not always writing the most optimized code in the world. Increments the index, and now I have to see whether I should continue my loop or not. I'll do a compare R1 with 1, not with R2. So is index less than 2 variable, and if it's less than or equal to, we are going to go back into our sum loop. So if if R1 happens to be equal to R2, that means we're at the last element of the array that I want to be looking at. And that means I go back into my loop. And then back when we get to the end, we can mov R0, R3. So put result in R0. That's our return. Okay. Oops. Let's see if this works. So far it's happy, that's good. Okay, so we got our array, should be in memory. I can just check that with the memory view, can't I? Memory, OX2, 000, 1, 2, 3, 4. So I can see my arrays here in memory. There's my first element. Of course, they're in little endian format. 03, 00, 6, 3, 00. There's my 8 elements. Now I'm going to read through my array. Got my from and to elements to go to. Oh, I haven't called the array sum function. Whoops. Lucky someone mentioned it. Do the stuff. Okay, now we're in the array sum function, setting up our result variable, setting up the size of each element. We're going to do our first offset, which is 0. That's easy enough. Get that value 2, add it to our counter, increment the index, compare BLE. This is fairly easy, isn't it? Where are we up to? Ah, good. We're out. And 0 is 14, so it worked correctly. A few... oh, some great questions happening in the chat right now. So there's a bit of discussion about what problems there might be with this function. Some suggestions are that, well, the first suggestion is that I didn't call it, but I've called it now. Second suggestion is that it's not push and popping LR, so that'll clobber it if it's nested somewhere. I suppose that's only needed if it's nested. Although, you know, our basic calling convention is to always push and pop LR, but in this case, I know that I'm not doing anything nested. I think the main problem, yes, it very much ignores CC. When someone has said I'm not supposed to use R3 to R11, well, I'm not supposed to use I'm not supposed to use R4 to R11 without setting it back to the way it was to start with. So in this case, I did a bunch of work in R3. That's fine. The calling convention says I'm allowed to do whatever I want in R3, R2, R1, and R0. But if I do things in R4, I need to set it back the way it was. So really I should be doing something like this. Push LR R4, R11 at the top. And before, when I come back, pop LR R4, R11, oops. And that would sort of satisfy the calling convention. Put in a breakpoint, run my thing, got 14, and everything is still happy. The R4 to R11 have been reset back to 0 in this case. Yeah, I don't really need to save LR there because I'm not using it for anything. I'm not calling any further functions, but I could need to if I had to call some other function. Okay, back to our lecture. We're a little bit behind because of that unfortunate internet issue, but I'm just going to show you a few different versions of this with a few hints and tricks. So in this first version, we can look at the efficiency of what we're doing in terms of how many instructions we're calling for each part of it. So we've got two instructions in the setup and 6 instructions in the loop. Okay, so can we do any better? Well, here's a different version. Now I've only got 1 instruction in the setup and I've got 5 instructions in the loop. So this is interesting. How do we do this? Well, in the previous version, I needed to have a register to store the size of each element in the array. And in this one, I haven't. And the reason is that I know that each element in the array is a multiple of 4. So really, when I'm calculating my offsets, I'm just counting by multiples of 4 or multiplying R1, our index, by 4 each time. So you can actually do this with a shifted index right in the load instruction. So the load instruction can do the load with an index and then shift it before it actually uses it. So it doesn't change R1, it just shifts R1 by left by 2 places, multiplying by 4, and then uses that result as the offset. So that's really handy because it can save me 1 instruction in the loop and 1 instruction in the setup. This trick only works if your array elements happen to be a power of 2. So it's something to consider in that case. If you've got things that are word-sized, you can definitely do it. If they're not, then you're, or if they're word-sized, they're likely to be a power of 2 in size. But if they're not, this won't work. Another option, this one's got 3 instructions in the setup and 5 in the loop. So in this case, instead of using an element index, I'm adjusting the offset each time and just using that single variable. So I'm going to do a little bit of extra setup in my a little bit of extra setup here, 2 instructions instead of 1. So rather than have an index in R1, which will be counting the number of array elements, it'll be counting the number of bytes I want to offset, and then the endpoint will also be the number of bytes I want to offset at the top of the array. And then every time I update my index, in fact, I'm just adding 4 bytes to it. So that would work too, no problem there. Again, this has got five instructions in the loop and 3 in the setup. So it's another way of doing our array. You guys could probably have a chat about different ways to speed this up, but there's lots of options for arrays. It's certainly something that you can have a hack at in your own time. There's a bit of discussion right now about what you might do in terms of knowing where arrays start and end. And that's actually a topic we're just about to get to. I wonder if I should do it right now or do it later. Well, here's one more idea about how to speed up an array. This is starting to get very optimized now. So we've got 5 instructions in the setup and only 4 in the loop. Now this might seem like it's bad, right? And previously we had 5 in the loop and 3 in the setup, so that was a total of 8 instructions. But the ones in the setup only have to happen once, and the ones in the loop are happening over and over again. So if we have to do a lot of loops, if we save 1 instruction in the loop, that's going to count the same as like maybe 100 instructions in the setup or more, right? If your loop is going through millions of times, you're saving a lot of instructions by removing 1 single instruction from the loop. So in this case, the idea is we can use the load with a byte offset, similarly to the previous example. So the index here, it gets changed into a byte offset, multiplying it by 2, multiplying the end offset by 2 as well. Then instead of using the start and end addresses, end ends as indexes or offsets. We want to get the actual location in memory where they are. So I'm adding the from an element to the base address and adding the to element to the base address. And then in my array sum, I'm actually going to add 4 to each address as we're going through using the post index form of the load register instruction. So this is loading the whatever is at the address stored in R1, our current address of interest, into R6, post indexing by 4, and then updating my running total. And so I don't have to do anything else to update my index. I don't have to multiply it. It just keeps going, and then I can do the same comparison, compare R1, R2, to find out if I'm up to that point in memory. So that's a little bit of extra optimization. Can save us another instruction. The idea with our optimization here is that loops in our code are something which is hot, so they're running over and over again. And if you optimize even a little bit in a loop, you save a lot of time overall. So, you may think that this looks weird, but an optimizing compiler will do some incredibly weird stuff to get absolutely the most optimized code. We saw in the last lecture, looking at the Godbolt Explorer, that optimizes the compiler will actually just evaluate your loop, and if it turns out that you're not doing anything, it will just delete it, right? So compilers can do all kinds of cool tricks to get crazily optimized code, which is excellent. In this case, we don't have a compiler. You're the compiler. You have to take the idea of the high-level idea and turn it into assembly instructions. And in that case, I probably would suggest that you write simple code first and then do the optimizing later, only if it's necessary. It's not a good idea to over-optimize things. And that would just be a general rule for writing code, specifically if you want your code to be understandable. When you're writing assignments, the main thing is that your code is sensible for us to read. If it's overly optimized, first of all, you may not really win back much time, and it might be much more difficult to understand what's going on. There's an obligatory photo of Don Knuth. Anytime anyone talks about optimization, they start bringing up the pioneers of computer science. This is my colleague Ben put this slide in years ago, and he said, has an invented quote from Don Knuth. I'm not sure if Don Knuth actually said this, but premature optimization is a pretty bad idea, yo. Not sure if that's a real quote or not. You guys in the chat can tell me if so. I think we're going to get back to some more of these topics on Friday, but I guess there's stuff we've discussed here already, which is thinking about endianness, thinking about how much we have to load and store from memory each time, thinking about bounds checking, thinking about our calling convention. So there's a lot of gotchas with data structures that we haven't quite gotten to yet, but you will need to confront them when you're writing your own data structures. I think we might leave it for the day here, as it's now 10:40. I think there haven't been any questions recently, so maybe we can just call it. If you've got more questions, we can put it up on Piazza, and I might run through the outro bit for a while. If you've got more questions, put it up on Piazza for us. We really love seeing your questions on Piazza. At the moment, things from our perspective on Piazza are a bit fractious because there's some students who are sending me screamers about assignment marks. Of course, we're here to give you more feedback about your assignments. We really want you to do great work, and we're here to help with it. But in many cases, the marks we give for assignments, we go for a reason, which is that we have an expectation of what work we want you to do. Oh, thanks, Kit. Great to hear that you enjoyed it. When we're getting back on Friday, we'll be looking at another kind of data structure or record, which is similar to what in, I guess, the abstract form of what in C you call a struct, where you have or different kinds of data. We're also going to talk a bit about memory allocation, which means I have to do a bit more research about memory allocation so that I can remember how it all works, because it's pretty interesting and hard. Hopefully I can give you a few interesting tidbits about how this stuff works in a real big computer. But for now, we can call today just about arrays.